So this lab is lab 5, and this is going to be associated with lecture 5, where we started talking about the first ideas related to evaluation. So let's write that down, lab 5, associated with lecture 5. Okay, let's do this. Okay, so we want to talk about evaluation in this lab, and we'll first work with a regression problem. So let's load up our favorite library, the math library, and we can load up our favorite data, Boston data set. And we can build a couple of models, and we're going to build up a couple of models using different transformations and different covariates. So all of them are going to be predicting the median home value, med-v, but we could predict it as we did originally from crime. So that would be one model. We could build a second model, maybe mod 2, and we could fit a regression predicting the median home value from maybe crime and the number of rooms. So RM is the number of rooms. And so I add a plus there to add on that covariate in my model. And what's another thing? We do mod 3. This could be median home value from crime and let's say the square of crime and number of rooms. And so we can build those 3 models, and then we can ask, for example, what the R squared value for each of those models are. So, for example, the model 1, R squared, is 15. The model 2, R squared, is 0.5. They're actually getting quite a high percentage of the variance explained. And the third model is 0.55, so even higher. So what's going on here? We should be careful because we are always, let's say, always going to increase the R squared if I add covariates. And this happens for other metrics too. So this isn't particularly R squared. You could look at RSS, you could look at wherever you wanted. But the fact is that if I add covariates, I'm just going to keep increasing my R squared. Because R squared in this case is basically the training R squared. And so I'm increasing the flexibility by adding covariates to my models. And therefore, I'm always going to drive down my training RSS or up my training R squared. So this is a bad way of choosing what covariates I should include. So let's say this is a bad way of choosing which covariates to include. And this is not a new problem. This has been known for a while. And this is basically the kind of problem of evaluation, the reason we do testing and training data. And so we can also look at this problem in terms of K and N. And this will give us a bit of a richer set of parameters to work with. It only has, say, the one parameter K, so it's easy enough to work around with. And we're going to work with our library FNN, so we can get our K and N regression going. FNN has this function, right, K and N regression, which lets us do our K nearest neighbors regression. And let's just generate some fake data for this. So let's say X, so let's just build it up. But let's take, maybe 100 uniform points between -1 and 1. Let's say if that were my X, I could plot my histogram of it, right? Basically, uniform between -1 and 1. But I really want this to be an array. First of all, for plotting purposes, it's going to be easier if I sort it. Won't change the distribution. But I want this to be 100 by 1 matrix. And And so if I make it like this, you'll see my matrix is 100 by 1, and those are my values. So I could even go like this, just print out x. So here's my x. Okay. So that's x, and we want to have some associated y. And last time we did y was x squared. Let's stick with that. And so I can generate, say, 100. I can generate a relationship y is x squared, and I'm going to add on some Gaussian noise, or some normal noise. So the R norm, and the three parameters, a number of points. I want 100 to match. And I want maybe from a normal distribution with 0 mean and 1/5 variance. And if I do this, I can plot x against y, and we get something kind of like what we had in the last lab. Okay. So how should I fit this? Last time we had looked at how to fit a K&N model on this. So how do we want to do that? How did we do that last time? We used our function way back up here, our K&N.reg. So let's say K&N mod, it's K&N regression, and train data was my x, test data I had as my x, which the data it predicts. Now we know kind of what the difference in testing and training is. We're going to have to change this in a second. And the training y, we had our value of k, maybe we said like 10. And so we could fit that, and you could even do plot x against y, and then you could add the K&N predicted line. So we'll add a red line there, and we'll plot that. And that's something like similar to what we did this last time. Okay, so now we really want to split the data into testing and training. So let's split the data into testing and training. And that's a little bigger than it needs to be. We don't even need that, do we? Okay. So notice in this case that I sorted my x's well, way back up when I had created them. And we can just look at the top. The first couple of these is just with the function head. Will give me the first 5 or so of these. We had sorted these, and that makes it easier for plotting purposes. But that's bad, or that can lead to some bad things if we do split our data into testing and training. Because if you naively just split your data in the first 50% of your testing and the last 50% of your training, or something like that, then we would accidentally include just like the lower values in testing and upper values in the training, and that would not be representative. So here's my idiom for splitting things. We're going to create a training subset. And the training subset is we're going to randomly sample half of the data. So this, right? Okay, so what this is saying, sample will randomly sample using 1 and the number of rows in X, and I'm going to sample 50% of them. So in fact, let's just cut this out and add it to its own little chunk here. So if I did that, so it's randomly sampling them, and I could similarly, I want my testing subset to be, so these are the rows of X I'm gonna sample for my training data, and my testing subset I'm gonna just choose as everything that's not in my training subset. One way I can do that is with the setDiff function. So I'm going to take the difference between 1 to n and whatever is in my training subset. And that will give me the test subset, that's the complement. So that's a little idiom for getting the complement and getting my train and testing subsets. And I'm going to use these kind of subsets to subset my x And so the way I could do this is it's going to be X. Training is my train subset. And I'm going to add on this little extra on here, say drop is equal to false, so that it does not, I might be able to demonstrate this. What that's going to do is it's going to keep it from converting my matrix into a vector. So you notice that X, to start off with, is a 100 by 1 matrix. And if I subset a certain number of rows, R is automatically going to turn into a vector. But that's going to cause problems when I pass it into my K&N regression function. If I specify drop as false, it keeps it as a matrix. So that's what that's about there. And let's move this on to a new line here. Testing data is going to be the same deal, but I'm going to say I'm going to subset to the test subset. And then my Y is similarly. And you know what? I probably want to pull these out as individual variables. Let's just actually pull these out as individual variables. So let's say train X is that. And so train X, this is just going to make it a little easier to read and more generalizable. What's called test X is that. Train Y is Y. And so let's actually add, what is Y? Y is also a matrix, right? So I'm going to play the same game. The reason I had 2 commas is because I'm going to select these certain rows, all columns, and then I'm going to not turn it into a vector. And let's say test Y is test subset. Okay, so I got my train X and train Y, test X and test Y. And then now this is a lot easier. Okay. So now when I fit this model, I'm only actually fitting on the training data, and I can test or predict on I could predict, for example, on the test data. And so these predictions are now going to be from the testing data. And what do I want to do? So I'm actually going to pull this out into a function. So let's pass it an argument called predict on. And what this is going to do is it's going to allow me to what do I want to do? I guess the question is K&N mod. Yeah, so this is going to allow me to switch out. Let's just call this predict X. It's going to allow me to switch out and use this function to predict both on the training data and the testing data. And let's actually call this function evaluate. And so it's going to fit the model, and it's going to fit it on whatever I tell it. It's going to fit it using the training data. Train X, train Y. It's going to predict on whatever values I tell it to predict on. And that's going to actually evaluate this. So if you look, it has a function. Has like an R squared. It has a residuals function. So if I were to evaluate this, we can also just calculate RSS individually. We can do that by ourselves, right? It's not that hard. What it is we'll pass another thing called predict Y. So what it is the predictions from k and n minus the true value, which we're going to call predict y. You square that and you sum it up. Okay, so here's my function called evaluate. It's going to fit the model on the training data, train x, train y. It's going to predict on whatever x I want it to. And let's pass it a capital K parameter, which will be the value of k we want. We can default it to 10 if we want. It's going to calculate the RSS, which is pretty easy to do, and then it's going to return that RSS test. Okay, so here's the big question. Okay, so here's evaluate. That's my function. Is this going to work? If I've written it correctly, it will work. So if I evaluate on test x, of course I need to say k and mod, right? And I need my predict y. There should be my RSS, assuming I've done everything correctly. So this is kind of a nice little way you can write this, and the RSS seems reasonable value given the value of our y's. Our y's are about between -0.5 and 1. So I've written this little function called evaluate, and I could also evaluate on train x and train y. So let me actually evaluate on those, but it allows me to go to a new one. Here we go. I could instead do this on train x and train y, and you should stop right here and say, what do I expect the answer to be? So this is returning to me the RSS. I've split my data into a training data set and a testing data set, and I have and then I'm evaluating on whatever, and I pass into it. I pass into both an x and a y matrix. It predicts, it fits the model using the training data, then predicts on the x data I pass in, be it training or testing or anything else, and then it returns me the RSS, right? So it should be that my training RSS should be smaller. Now, watch, it's not going to be. It doesn't have to be 100% of the time, but typically it's going to be. And it is, right? So here you start to see what's happening, right? My training data, by evaluating my RSS on the data that I use to train the model, I'm overly optimistic with the performance of the data on the performance of the algorithm on a new set of data. Okay, now we can have some fun. We've written this little function, which is a fun little function, and that's a nice little idiom. You can basically swap out, k and n for whatever else you want, and you can use this to evaluate, your methods here. And so one of the questions, of course, is how we choose this parameter k. I've defaulted at 10, but there's no, that's kind of an arbitrary choice here. So how should we choose this capital K parameter, right? Okay. So as we saw way back for the regression models, if I just kept increasing the complexity of my model, that is, if I kept adding variables and kept increasing the size of my design matrix, it just kept increasing R squared. You could also look at RSS. It would decrease RSS or increase R squared. And indeed here you could replace this with R squared if you wanted to. You would have to calculate the total sum of squares, which wouldn't be too bad, but one could do that. Okay, so if we just evaluate in the testing data, if we only evaluate the training data, it's probably not going to be a good way to choose k. But again, let's just look at it. So we could set a sequence of k values. Let's say 1 to 50 by 5. So we'll create some different values of k that we could choose. That looks cool. And we could evaluate. So let's say train RSSs, right? Okay, so the training RSSs. What do we want to do? Basically, we want to call our evaluate function on all these different. Now, one way you can do this is write a for loop. You all know how to write for loops. I think there are interesting ways to use the apply family of functions in R, which is a kind of functional programming way of writing it. And basically, what it says is I'm going to apply to my case sequence, my sequence of values, this function evaluate. So I'm going to apply evaluate to 1, 6, etc. Of course, that's not quite what I want to do here, is it? Let's just write a for loop. That can be easier. No, you know what's going to be easier? We'll pass it. So I'm going to apply it to this function. I'm going to evaluate. Okay, so here's what's going on with this call. To this case sequence, I'm applying this function. And this function is going to take an argument k. It's going to call the evaluate function, pass in train x and train y, and then I could even write it like this. It's going to pass in my value of k, right? That I'm going to use to fit my k and n model here. And so if I call that, it's going to give me my training RSS for each of these. That's pretty quick to evaluate, so maybe we can increase our k sequence, make it something even more interesting. Uh-oh. What did we do? We broke something. Had to undo. What could we possibly have broken here? Works for that sequence. Strange. But if I go like that, and index out of I can't actually go up to 50, can I? Right? Yeah, I can't have actually that sequence before, right? When I went by 1, it goes up to actually 50. I only have 50 points, so it's going to cause an error here. So let's go to 49. Okay. Is that what's going on? Or not. What's going on here? What's going on? Same thing. That works. 2, that works. Why would doing 1 break it? Well, we'll think about it. It's possible it doesn't like even numbers. One way to test that is, oh no, it worked with 10. So that's weird. One way to test this, so we'll do some real-time troubleshooting. I'm just going to have my function print out the value of k. I passed it. And then we're going to see if I do this, fails on 1. Well, ain't that something? It doesn't like 2. Yeah, I think I remember this. For some reason, it doesn't like 2. This is a bit of a quirk, isn't it? Whatever, let's do our case sequence starting at 2. This should work. Let's not screw around with this anymore. Okay. One way we can do, yeah, let's just leave it like that. And then we'll get rid of this print line here. Okay, nope. Gotta get used to Jupyter. Okay. Okay. So let's just work with these. For some reason, this k and n regression function doesn't like 2. It's never like 2. I don't know why. Okay. Now we get to train RSSs over a little bit more. Okay, here are all my train RSSs. But that's a weird way to write it. So let's plot my k sequence against these. And here's what it looks like, okay? So if I let's zoom out a little bit here. Of course, I want to zoom in a little bit more than that. Can I zoom? Whatever. Okay. So the point being is that if you look at my training RSS, it monotonically decreases as I go from larger values of k to smaller values. Indeed, as I claimed, if you look at this thing evaluated at, not 0, at 1, it has an RSS of 0, right? So my RSS is not exactly 0 out of 3, but if I put it at 1, and we mentioned this when we talked about K and N, is that it will give me an RSS of exactly 0. You'll interpolate my training data. Now notice that, so basically it's always going to tell you to choose smaller and smaller values of K because it's going to better interpolate the data. And here, is their train RSSs. So this kind of answers a question about how do you choose K. One way you could do it is this way, but this is particularly a bad way of choosing. It's just going to tell you to choose the smallest value of K possible. That's not a great idea. Notice that if we do this, so we can basically redo this whole thing, and instead of train X and train Y, we can look at test X and test Y. That does not have a 0 RSS at 1 because it's not being evaluated on the same data. So interpolating testing data, interpolating training data is not necessarily the best way to predict new unforeseen data. But interpolating and testing the training data is the best way to interpolate the training data, to do well in the training data, right? So this training metric, evaluating the training X and training Y, is misleadingly not great. So we could play this whole game again. Let's just copy this code here. But instead of on train X and train Y, we can have it on test X, test Y, and we call this test RSSs, and we can plot my test RSSs against that. And now we see something more interesting. Now it actually appears with this data you can do quite well with a smallish value because it's pretty complicated data. It looks like somewhere around, well, that's what 1, 3, 5 is going to be the best value, but it's not 0. It's not great up here, but it has a dip here. And so one thing that you could do is you could say, pull out the K sequence, which has the minimum value of my test RSSs, and call that K hat. It's going to be my best K. In this case, it's 5. Then I could rebuild my K and N model based on that. So let's say best K and N, train X, test is this how we do it? Let's just copy the code from up here. So that's gonna be a lot quicker. Right. Train X, train Y, and let's look at my test X. And K, we can pass it K hat as my best one. And what do we want to do? We could plot test X against test Y. Okay, that's what it looks like. And then we could add our predicted values for these. Looks something like that. So it's predicting on, test is hexa. Yep. So that's my kind of best model as it predicts on some new data. And we can even make the color red here for fun. So it's not the simplest model, but it does a pretty reasonable job of capturing that with not a lot of data. It's a pretty low value of K, and we can talk more about that next time. And we can develop, we'll talk next time in the next lab about cross-validation, and we can develop a little more complicated scheme of choosing it. But we're kind of out of time now, and this is a great stopping point here. So this lab is to show you that evaluating on training metrics is always misleading, or can be misleading. You have to be very careful about it, right? And so things like linear regression, it says, ooh, well, it calculates R squared for you, but that's a training based R squared, right? And so it's misleading because I could always just add more covariates. And we could have this whole discussion in terms of how much covariates we add to a regression model. We had it in terms of K and N because it just has this one parameter that we can play with, so it's really easy to demonstrate this all. And so what we did is we generated their data here, and we built this little evaluate function, which allows me to train on my training data, evaluate on some data I passed to it, along with my tuning parameter K, and it will return to me the RSS. And so you can see for my training RSS, it just gets driven down as K decreases. So it's not a great way to choose the value of K. If we instead do the test RSS, at least in this case, you're going to choose something that's not identically 1. And it looks to be about 5 here for this data. And you could fit that model and kind of plot it there. So I'll stop here. Next time we'll talk about cross-validation and nested cross-validation, how to do that.